Each year, car crashes result in thousands of lives lost and hundreds of thousands of injured victims. By capturing the data resulting from these crashes, it's possible to better understand the risks that are associated with driving and to make more informed decisions to help improve driver and pedestrian safety. Data mining offers the ability to derive insights from complex data sets, which can be used to make more data-driven decisions to help find solutions to challenges like roadway safety. Our objective is to apply the data mining process to the NHTSA car crash dataset to create predictive models that will effectively identify underlying variables that influence the severity of a car crash. Following the CRISP-DM process, our goal is to analyze the dataset using the NIME Analytics platform to gain insight into the factors that impact the severity of car crashes. Our project will follow the structure of the cross-industry standard process for data mining. We'll begin with an overview of the business problem and our specific goals for the project. Next, there'll be an overview of the dataset we'll be using and the necessary steps taken to prepare the data for modeling. And finally, this will lead to a review of the impact and success of our predictive models. Our goal for the data mining process is to discover what variables influence the nature of car crashes, and to predict and explain the severity of each crash based on the variables found in our dataset. To accomplish this, data mining will be applied to build models that can predict the value of our target variable, the severity of the car crash. By analyzing specific variables found in the dataset that describe the nature of each car crash, things such as location, weather conditions, or vehicle type, we'll determine what variables influence the output variable. The success criteria used to evaluate our results will be the level of accuracy our models achieve. We want our models to achieve an overall accuracy greater than 80% and a sensitivity level greater than 50%. By reaching these metrics, we believe that our models will produce results that are sufficiently accurate and reliable to be confident in the conclusions they present. The dataset we'll be using in our analysis is provided by the National Highway Traffic Safety Administration. The data was compiled through a sample of police-reported crashes involving all types of motor vehicles, pedestrians, and cyclists. This data ranges from property damage-only crashes to those resulting in fatalities. The dataset was drawn from a nationally representative sample derived from the more than 7 million police-reported crashes which occur every year. The dataset contains elements from 3 different sources that describe the individuals, vehicles, and accident characteristics involved with each incident, each containing more than 50,000 rows of data. The overall data completeness is very high, with many columns containing no missing values, while some of the highest missing percentages are roughly around 25%. We believe that the quantity of data present, in addition to the high completeness, will allow us to draw accurate conclusions from our analysis. Because of the large number of variables contained in the 3 source files, it was necessary to narrow down the variables that would be used in our analysis. After reviewing all the variables present in the dataset, we identified 21 along with the dependent variable that we considered to be the most promising for creating our data mining models. Because many of the variables describe similar characteristics for each accident, we selected our variables so that they would cover as broad of a range of factors as possible describing each incident, with the end goal of predicting the value of injury severity. After selecting the variables that will be used in our models, we completed basic statistics for each variable to confirm whether it remained a viable option for our models. The statistics we generated using the NIME Analytics platform included the minimum, mean, median, maximum, skewness, kurtosis, and number of missing values. Upon reviewing the basic statistics for each variable, there was no indication that any variable was unsuitable for grading models. Each variable contained very few missing values and confirmed the quality of the dataset. Some of the statistics that appear to be outliers, such as the high standard deviation for a vehicle model year, made sense in the context of the situation where there would be a wide distribution of vehicle years among drivers. Based on the statistics that we computed, we found that the selected variables remain suitable for our analysis. The target variable we'll be predicting, the severity of each injury, is a numeric value in the dataset that contains 8 possible values, each describing the nature of the outcome. The levels of severity range from no injury at all to fatalities. Additionally, values are recorded where the level of injury is uncertain, with the value 1 representing a possible injury, 5 an unknown level of severity, and 9, either an unknown or unreported injury.
So to start the process, the person table, the accident table, and the vehicle table were joined. In order to join these tables, we needed to link them on their identification numbers. So person and accident were joined on case number, and vehicle and accident tables were joined on case number and vehicle number. Once this was accomplished, did we need case number, person number, and vehicle number? Well, we didn't want those to be in the data sets as independent variables because they had no predictive value and they would add a lot of noise. But if we want to join ROC curves later in the process, then we need them to join the tables back up to spit out that information. So what was done was that row ID was created by joining case number, vehicle number, and person number into one variable that we named unique ID, and then set that to row ID and excluded the original identifiers. Then we moved on to variable selection. There were many variables to choose from, and we wanted to narrow it down to between 20 and 30 variables. So this is the list we ended up with. Some of them were just kind of month and hour. Those are good because hour, for instance. Are there more severe injuries at night after the bars close? There you go. Some of them were real no-brainers, like ejection. If you get ejected from your vehicle during a crash, odds are your injuries just went from minor to severe real fast. Or if your car explodes. So we've got fire, explosion. Did you catch on fire or explode? Yeah, you probably got hurt pretty bad. So that kind of common sense, that kind of just our own judgment was used. We also read Dr. Dellin's example papers and kind of gleaned some knowledge from there and used the crash manual to help with the process. We wanted to include a measure of vehicle mass and a measure of speed so that we could kind of get an implied force of the crash. So we included gross vehicular weight and travel speed. And then, injury severity as the dependent variable. So injury severity was our target variable. In its original form, there were 8 possible values for this variable. No apparent injury at about 68% of the data, possible injury at 14.5%, suspected minor injury at 7.7%, suspected serious injury at 4.9%, fatal injury at 0.7%, and then there were the kind of unknowns or died before crash, and those were about 3.9% of the data. So the original data set before treatment of the target variable had 133,408 observations. Because injury severity is our target variable, we want only known severity levels. So severity unknown, died before crash, and unknown not reported were excluded from the data set. Those 3 variables, again, were about 4% of the data, so their exclusion left 128,213 records. Once that was accomplished, we used the number to string node to convert injury severity to a string value, and then created 2 categories, minor and severe. Minor being no apparent injury, possible injury, and suspected minor, and severe being made up of suspected serious and fatal. Next, it was time to start aggregating and categorizing and just kind of grouping up variables for better processing efficiencies. No variables were imputed. The only excluded observations were those in the target variable that did not identify injury severity. The decision was made to collect unknown and unreported values for each of the variables into a separate category, allowing us to keep the maximum number of observations for the modeling process. So in some cases, they were real simple, like fire and explosion had two possible choices, 0 being no and 1 being yes. So we ran them through the rule engine, got a binary no yes variable. There were quite a few like that, fire explosion, rollover, ejection, although ejection did come in varying degrees. And so a lot of very straightforward translation of numeric to string, just taking, for instance, month and converting it from the month number to the month name. In some cases, and in many of the variables, there were a really extensive, large number of possible values. They were aggregated into groupings with fewer values, such as, for example, a really standout example was the make of the vehicle. The user's manual for the dataset contained pages and pages of possible values for vehicle make. We reduced that to domestic, import, motorcycles, mopeds, large trucks and buses, and then the other unknown, not reported category. Vehicle size was considered a very important factor because it's a determinant of the force of the crash. Gross vehicular weight rating was selected as the variable that we were going to use to put the vehicle mass into the model. Unfortunately, that variable was 96% not applicable, unknown, or not reported, and it led to models in our testing phase that just couldn't predict injury severity at all, or not very well. So, body type was added because it's another way of indicating the vehicle size or mass. Body type classifies the vehicle's approximate size in 99.6% of the observations. So adding that variable actually it increased the prediction. It decreased the number of times that the model just could not spit out a value. Seat position is another variable that was kind of treated in a different way. Seat position gives the position of the vehicle occupant as side plus row, so that each record would tell you which side of the vehicle and which, like how far forward or back in the vehicle a person was. And that is a good piece of information, but it was decided that we should isolate it a little further. So seat position was broken into two variables to get row and side. So now you have a variable that tells you how forward or back a person is in the car, and you also have a variable that will tell you whether they're on the left side or the right side. So once we did all of that pre-processing, everything is converted to string values, it's been aggregated as needed, it's ready to be fed directly into categorical type models such as trees, KNN, knife, bias. And then two further steps were needed to be able to make the data ready to be consumed by numerical models such as neural networks and logistic regression. It needed to be converted to numerical values, and those values needed to be normalized. The one-to-many node was used to convert all but the target variable to numeric value. And then the normalizer node was used to perform min-max normalization on the data so that all the values were converted to a range from 0 to 1. And now we'll turn it over to the modeling process.
As Lori mentioned, some models were ready to begin being partitioned from the final filtering node, and others needed two more steps in order to be run through a particular modeling node. Modeling types RPROP, multilayer perceptron, logistic regression, and k-nearest neighbor required that we first run our filtered data through the one-to-many node and then the normalizer node. This gave us data that was all zeros and ones, with 0.0 being the minimum and 1.0 being the maximum, and then those models are ready to be run. The remaining model types were ready to be partitioned straight from our final filtering node. Now, all nodes are ready to be partitioned. Each partitioning node was identical so that we could achieve consistency across models. For each partition, We selected a relative percentage for our first partition, which was 70%. This went to the learner node, and the remaining 30% of the data went to the predictor node. Next, we selected to use stratified sampling of our dependent variable, injury severity, so that the number of severe and minor categories were equal percentage-wise in the learner and predictor nodes. Finally, we chose a random seed of 1, 2, 3, 4, 5 for further consistency across the nodes. Seven different nodes were selected for modeling our data, each of which involves slightly different setups and results. First, the nodes that were run with normalized data, the RPROP multilayer perceptron learner, logistic regression learner, and k-nearest neighbor. For each of these, the class or target column of injury severity was selected. On our RPROP MLP learner, we selected only one hidden layer. For the logistic regression learner, our solver was stochastic average gradient. We also increased the epochs on the logistic regression learner in order to increase the predictive quality. On the k-nearest neighbor, we selected to have it consider the 3 nearest neighbors. Next, the remaining 4 nodes that did not require normalized data, random forest learner, decision tree learner, gradient boosted trees learner, and naive bias learner. Again, the predictor nodes on each of these injury severity was selected, and that was selected as the target classification column. On the random forest learner, our split criterion was information gain ratio. For the decision tree learner, our quality measure was the gene index, and we had to increase the number of records to store for view up to 50,000 in order to have no excluded columns or rows. On the gradient boosted tree, we use the default settings. For the naive bias learner, the maximum number of unique nominal values per attribute was increased to 60 in order to have enough bandwidth in the model to cover all possible variables that we wanted it to run. With the models we want to use now selected, we can move forward into evaluating the results of our respective models via accuracy on the confusion matrix and in the area under the curve data. With our models executed, it's time to see what the score and ROC curve nodes showed for each model type. First, the confusion matrices. Here are the confusion matrices for each of our model nodes. The accuracy in each of these is above 90%. Here are the ROC curves that were generated. These, of course, include the RPROP multilayer perceptron, the logistic regression, and random forest. Here are the ROC curves for the decision tree, the gradient boosted trees, and the naive bias model. So now we have further evaluation with our model comparison. Below is a side-by-side comparison of all models. On accuracy, the multilayer perceptron with regular 70-30 partitioning, it comes out best with 95.2% accuracy. Based on the area under the curve number, the multilayer perceptron also was the best with a value of 0.8629. However, Due to the extremely unbalanced nature of the target variable, and so all of the data was 94%, 94.3% was minor injuries, and only 5.7% of our data was severe injuries. All preceding models are much better at predicting minor injury than severe. Since the purpose of the study is to predict severe injury, balancing is needed to boost the prediction of the severe class. To attempt to accomplish this, an additional neural network model was built using SMOT, synthetic minority oversampling technique, and tenfold cross-validation. Here's some screenshots of our model. With this model, we were able to achieve over 50% accuracy predicting the target class, as well as over 85% accuracy. While this model may have a lower overall accuracy than the other models, this would be the model we choose to deploy due to its improved sensitivity. Here's a final model comparison, which includes our final improved model with increased sensitivity. As you can see, the per class accuracy on the severe injuries is almost double increased accuracy than the next best model, and many times better than say model 1, which was 6.47% accurate on severe, and model 7 62.83 accurate in predicting severe injuries. We also wanted to mention our variables and their significance. Ranking of variable importance using split and candidate data from the random forest model shows that ejection is the variable with the most impact on injury severity. This is followed by travel speed, fire/explosion, rollover, and model year. Person type had no discernible effect on the model, and other variables such as gross vehicular weight rating, age, seat position, both side and row, month, and number of lanes had very little impact on the data. With our best model selected, this added multi-layer perceptron model with the X validation and SMOT oversampling will be what we wish to use going forward. We will use this model not only to increase our overall accuracy, but also to increase our accuracy on severe injuries. Our goal will be to deploy the model so that we can help car makers and insurance companies identify the factors that lead to severe injuries in car accidents so that we can help prevent them in the future.